for the summary of week 3, I want to look at the birthday problem. The birthday problem is a very classic trick problem in mathematics. So what does it ask? Well, let's say you have a group of n persons. What is the probability that at least 2 of them have the birthday on the same date? So they share a birthday. And by the same date, I mean the same day and the same month, not the same year, of course. So if your group is small, the probability is very low. If your group is large, the probability is very high. Many people find the result unexpected. The main result is that you only need approximately 23 people you only need exactly 23 people to reach a probability of approximately a half to have a collision. So many people find this number surprisingly low. So we'll implement this in the summary today. I hope you enjoyed the dedication. For information, she seems not to be here yet. Okay, so let's summarize the situation. I'm now in a folder, and I have here the birthday.py file that you see right above. And this birthday.py file is a Python program, a full Python program. So I'm not using the interactive mode here. I intend to run this full program at once. So what do I do here? I import the random module. So we've seen this at some point in the lectures. And I will use the random module to generate random dates of birth. And I'll perform an experiment many times, or actually indefinitely many times as the user wants. And what's the experiment? The experiment is to take a certain number of groups, and in this case 10 to the 4, so 10,000, and a certain number of groups of the same size, and the size will be determined by the user. And I pull a day at random between 1 and 365, and I see if that birthday has already appeared in the group. And if yes, then I count that as a group with a collision, and if not, then I count that as a group without a collision. And I do this experiment 10,000 times for that particular group size, and then I report the result. And then I ask for a new group size to perform the experiment again. So let's see this run. So I'm running Python birthday.py, and I'm asked for a size of a group. So let's see the result I told you. If I have a group of 23, then the program found a proportion of 0.4948 groups without collisions. And this is out of 10,000 different groups that were tested. Now think about it. If I take groups of size 10, then the probability of not having a collision will increase. And so you should see a bigger proportion of groups here without a collision. So let's see that. And indeed, you see that there is almost an 89% chance that a group of 10 persons does not share a birthday. Or at least that's the result of my experimentation. I shouldn't say that there is a probability of 89. I'm just simulating this problem here. So what if now the size of the group is 50? Well, in this case, it becomes very likely that there is actually a collision. So let's see how many groups do not produce a collision. Well, only 3% of the groups do not produce a collision. So the computer simulated 10,000 different groups and only found 300 of them that didn't have collision, 298 to be precise. So if I take a group, let's say the size of more or less the class, so maybe a bit short of 100, a group of size 90, then my program is simulating and does not find any collision. So this means I could run my class 10,000 years, and with a group size of 90, there will always be a collision in practice. Okay, so there is a chance that there would not be a collision, but I might try for 10,000 times, and it seems that this is here. The first time was not producing any collision, and the second time only one group produced a collision. Okay, so let's see how this was implemented. So first of all, the program consists mostly of a while loop. And I say while true because I want this to repeat indefinitely and forever, essentially. Okay, so what do I do in there? Well, I asked for input from the user with the command input, and you saw this in action, and this is assigned to group size. And I prepare some variable without collision that will count the number of groups that haven't had a collision so far. Now for every integer in this range between 0 and the number of groups I wanted, -1, so for 10,000 integers, and those will be group IDs, I prepare a list that will be all the birthdays encountered so far. So at first this list is 0 because this list is empty, because no member of the group has entered my picture yet, so I have no birthday to take into account. But I start doing this here. So for every person in the range of the group size, I will produce a birthday, and I'll assign to the variable named birthday some random integer between 1 and 365. Now I do a test. If the birthday is already in the list of encountered birthdays so far, then I break and think hard about what this does. This breaks from the innermost for loop. So it means finish this experiment and go on with the next one. Use the next group ID and perform the experiment again. Okay, so this is what this break does. Now this only happened if the birthday was already present in the list. What if the birthday is not present in the list? Well, then it should just be added. Okay, so you have your calendar with all the different birthdays written, and you just add it to it, this new person's birthday. So this is the innermost for loop, but what do we want to happen? What else do we want to happen? Well, if we run through the whole group size and we never encounter a collision, then we'll just repeat, and then we'll be done with running this for loop. But in this case, we want something to happen. This is the else clause here. We want, in that case, the number of groups without collision to be increased by 1, because we just found a group that never broke here, that never produced a collision. So we need to add 1 to this count. Okay, and this part here is all the part that's repeated for every group. So for every group, the result is that I might add 1 to without collision, or I might not. So the conclusion is that this print statement here that I have here, in the end, will print for that many people, I found a proportion of this many groups without collision out of performing the experiment on that many groups. And this is what you saw here in action. So if I take a group of size 40, then I perform the experiment, and 11% of them, 11% out of my experiment didn't have collisions. Okay, just a few comments about this program. So 2 comments first. First is I've here used group ID, and if you look carefully, that word only appears at that location. Okay, so I have never reused group ID anywhere if you look carefully. So for the program, this could be named anything you want. It's completely superfluous. The only point of naming it group ID is that it helps understand what that is meant to do. So it's kind of an explanation for the human reader. If you don't want to provide this explanation, you could have used this. And this underscore here is a completely valid variable name, but it's kind of a convention among Python programmers that this underscore means some variable whose name I don't really care about and I will not reuse anymore. Of course, you could reuse it, but because it's a perfectly valid variable name, but the convention is kind of that you won't reuse it. So this is more like the human side of programming. A second remark is that I've made more effort in this program to document what's going on, to indent properly everything, and to put the spacing everywhere I should, and to avoid long lines and things like this. So for instance, I've used the slash here to avoid having one long line with all the elements I want to put in. The reason is that this is following some standards, which are explained in the extra section this week. This is following PEP 8, or following some of the principles of PEP 8. And this is really good practice, as I explained in those extras. So I'll refer you to those extras now. Okay, so those are all questions at the programming level, or remarks at the programming level. I want to make a few more remarks at the mathematical level. Given this program that experiments for you and performs a simulation of a theorem, essentially, you should ask yourself a lot of questions. And I've listed them here. So I'll read through them very quickly. If you increase the group size, does the proportion of groups with or without collision transition slowly or sharply from a value close to 0 to a value close to 1? So do you think it will happen quicker around 23, or it will happen quicker around 50, or quicker around 10? So try to plot in your head this proportion as a function of the group size. Okay, so that's the first question. To explain the later question, it helps to fix the group size at 23, let's say, momentarily. So you can perform the experiment with group sizes of 23, but you can also play with the number of groups. So what happens when you increase the number of groups? What happens to the calculated value? And the answer is that it will seem to tend to a constant. So there will exist a limiting constant as the number of experiments performed increases, and you can look up what the value of this limiting constant is. So now let's look at this limiting constant, and actually let's look at the difference between the value we obtain and the limiting constant, what we will call a deviation. So if I increase the number of groups, I just told you about before that the deviation should tend to 0. But you should ask yourself as well, how fast is this convergence to 0? And more importantly for this course, how would you test it? So this you can ask for a group size of 23, but you can also ask the same questions for different group sizes, and you can see how the answer of those questions varies as you change the group size. Also, you can consider a completely different problem, or an extension of this problem of simple matching with the birthday problem. For instance, you could ask for what is the probability that 3 people share the same birthday? Okay, so triplet matching. Or you could ask for the probability that 2 pairs of people share birthdays on the same day, instead of just asking for 1 pair. So the goal in this course is really this. It's really to give you, as here, the tools to perform one experiment. That's one part of the course. But another very important part of the course is that I also want you to ask those questions. I also want you to think for yourself about interesting questions to ask and interesting questions to implement. And this is the direction that we'll go in with the projects. And with the projects, I will really want to encourage you to think of questions like this and to implement them on computer. And then I'll give feedback on the implementation itself and the questions as well. So this is a little preview of what the projects will be about. I know you guys are curious about it, and I took the opportunity here of the summary to present some of those ideas behind the projects.